Hello and welcome to another tutorial for KiMoPack. For this tutorial we are going to discuss the advanced fitting options and how to use all of the different modules. We're going to use the TA Advanced Fit workflow tool, which you, as all of the other modules, can download from GitHub, either by going to GitHub or by using the download notebooks function. After import, we load a data file, and here I use an HTML5 file because it contains already the sharp correction and all the slices, but of course you can load other files before and then shape them in the usual way. All functions in KiMoPack are called separately, and you can copy paste that from one notebook into another. In the basic fitting tool, we had imported a module by calling the module TA mod and gave it a name. Here we actually give our fitting tool a function which we load from an external file. In this case, you can of course also write the function inside the same notebook as is done in the tutorials. Here I import the function library. And this I do because we provide a function library with a large number of predefined functions, which you can use as either an example, they're very well documented, or use them directly. In addition to the function library, there is a PDF where all of the functions are shown and described. So the built-in, for example, the built-in models, where you have the parallel, you have the sequential models. At least the sequential models have the option of an infinite state. Same also for the built-in model, and of a background fit, where you could, for example, turn on the word background and then you fit the background, or turn on the word infinite and you fit the infinite. I'm going to show you that in a minute. Then you have the example functions, where, for example, there's a manual written consecutive function, which is in here. Each function itself is defined, so it has a name, which needs to be unique, at least in this file. It takes a vector of the time, and it takes a parameter object. Then inside this function, you need to generate something which is the C, which is a data frame, which contains in the columns the different species, and in each row a different time point. You have the option of naming your columns. The names will then be used in the plots to define what are the different species, what is the names of them, and this is used in all plots, very useful. For defining the kinetics or the time development, I commonly use differential equations, where we generate a pulse or a sample, a pulse. This can of course be also a measured pulse, doesn't matter. And then I write a differential equation, which is the decay of the function. You can write any function you want. You can use any input data. I have successfully, for example, used data from Potentiostat for describing spectroelectrode chemistry data. In the example file, there are consecutive, there are square dependence, also ein decay which is dependent on the intensity by a square factor, for example annihilation processes, and one distributed rate model where you have a central rate and you have a rate spread for describing the dynamics. In addition, there is a number of different processes or different model functions described, each one with a name. And to show you how to read that, you can, for example, to use that function, you would need maybe use P12. Where's the P12? P12. We would need, for example, we pump, and we have 1, 2, 3 decay processes with the labels K0, K1, K2, and we have 2 species of which we fit as a model, If you give the word infinite, you add an infinite model. If you give the word background, you give a pre times 0 as a species. Now to use this function, what we do is we define fit parameters. We have our K0, K1, K2. If you wanted to add an infinite non-decaying component, then you would, for example, add an infinite, and then you have an infinite component. It just looks for the keywords. There doesn't need to be anything in it. For each parameter you add, as in the standard functions, you need to add a value, which is used as a standard, as a start. So you import your function library, and you define the parameters as in the standard fitting, and you call fit global, and it does the fit. Once it's done, it will give you the values, it gives you how close it is to the borders, if you set any borders, and you can plot, of course, the fit output in the same as in the standard function. In addition to this approach where you write your own model or use one of the predefined models, you have a number of optimization possibilities. For example, you can dump the parameters. That means when you interrupt, you don't lose what you have already fitted, what is your optimum. You can, this one dumps one file for the current parameters and one file for the minimum. You can dump the shapes. This is the current concentrations or the time development if you want, and the current spectral, or decay associated or species associated spectrum. This is very useful because, for example, in your example function or in your development, you can load the external files. If you fit multiple datasets like that, you can very easily hand, for example, certain spectrums. You have the option of, for example, loading in an external spectrum, either doing that in your example file, or much more comfortable, you load it inside this notebook and hand it to the fit global as external spectrum. Important, the column name must match a species which you have used. So if you use your own species, define them, for example, let's take these ones, P12, our example function, then you would need to, for the species A to be replaced by an external, for example, electrochemically measured spectrum, you would need to create a column with the name A and then give that to the function. The fit function will interpolate the measured spectrum and sample it on the same positions as your transient absorption. You have the possibility to optimize the chirp. For that, I recommend to make a copy, because that goes wrong in 1 or 3 cases. If you make a copy of the file, if it's successful, we write it back. If not, we can just try different parameters. You can do an error analysis in which all of the parameters which are allowed to vary, so which have vary equals true, are tested step by step, moved a little bit. All of the other parameters are optimized to find what is the limit, the confidence limit of these parameters. The cutoff is defined by the confidence level and by an F-test using the variance and the numbers of parameters. Very powerful is the option to fit multiple datasets at once. This is absolutely crucial if you work with solid materials. For example, annihilation processes and similar things are typically tested at different pump powers. So for that, I use pump power dependent measurements and, for example, load a different pump power as a different dataset and add it into a list. There are typically these 3 different ways which I use. Either you load it by hand and put it in a list. You use other data objects where you take exactly this kind of list comprehension which we have here, and then add, for example, file names, for example, sample3.htf5, right? Again, pre-shaped data into the other projects, and there's of course a GUI option where you just click on the other projects. Now, other projects is a list of projects which are opened, and this list I can give to the fit global. As a multi-project, I give this list, and now all of the models will be fitted independently, but using the same parameters. So it will be for each of the models will be fitted with this specific parameter. Then the error of that model will be summed, and this will be used as a feedback to optimize the parameters. All parameters which are set to vary can vary, and all of the projects get the same parameters. Exception if I define unique parameters. These parameters are kept. Now, this would be, for example, used if you define, for example, here, define a unique parameter, par.add. Let's call that F0. Value equals 5. Now I can use this parameter in my model. For example, let's go to the square dependent model. There I use the F0 parameter to multiply this on my Gaussian, which represents my pump power, and suddenly I have a power dependent process. I can choose different pump powers. For these optimizations, I can also give weights, which is very useful if you don't want to scale or multiply, manipulate your data. For example, for the pump power dependent measurements, I usually give weights corresponding to the pump power to correspond for the different noise levels and signal strengths, of course. Important is for all the standard approaches, each of the three datasets will be fitted, or the error and the spectrum will be calculated independent. So they can have independent decay associated or the species associated spectra. I use it as a check afterwards. I compare the species associated spectra. If they're very similar, that's very good. It's an indication that I trust the model. If they're very different, then I have to look a bit closer of what is going on. If you do not want that, there is a keyword same DAS. Then you're forced to use the same DAS, or better, you calculate the DAS for all of the other projects, everything with us as a project in there at the same time, and you find the DAS which is optimum for all of them. There is a global minimum search which uses AMPGO. AMPGO is a tunneling process manager which checks in the limits of the parameters and uses different starting parameters and then does an optimization. Internally, I use NeldMeet as a standard optimizer. If you switch to AMPGO, you use locally NeldMeet, but use AMPGO as an external one. Important is for all of those global minimums that you define for each parameter, which can vary, a minimum and a maximum, because it needs to know in which range it needs to check. Careful, this can take very long, typically 200-400 times longer than a normal optimization. This is the same for the confidence level. Confidence level calculations typically take 150 to 200 times as long as a normal optimization. On the other hand, a normal optimization goes relatively fast. As an example, if I disable the parameters I didn't want, and I start that, you can see that the code is optimizing. It prints out the error, and it is relatively fast. Typically you need 50 to 100 optimization points before you reach that. So that's like 1-2 minutes, which means that confidence interval calculation can take 1 to 2 hours, but it gives you a very nice confidence. If you use parallel model, confidence intervals typically takes a few seconds. That's all for today. I hope you had some fun, and until next time.